Hello, good evening. This is our EASY lecture series. Name is Boris Jeremic, professor at UC Davis, currently in Zurich, Switzerland, sabbatical at ETH. With me is Dr. Han Yang, who will be talking about energy dissipation, continue his series of talks on energy dissipation. And today he will be talking about energy dissipation by means of algorithmic damping, numerical damping. It is Tuesday, May 26th. It's 8:13 p.m. 2013 in Switzerland, and it is 11:13 in Davis, California.
Yes.
Where I understand it's also getting very hot.
Oh my God! Today is 103 degrees outside.
Oh boy! Oh, that's 40. That's 40 centigrade. That's okay.
Yeah, that's almost
so,
40. Yes.
Han, please go ahead, share your screen. Let's go with the lecture, and we'll go back.
All right.
Mr. Heshen Wang is absent because he had a meeting on his teaching assistant position, so he will join us next time. Go ahead, please.
Okay. Let me share my screen here. Full screen. There we go. All right. Okay, here we go. So today we're gonna continue our topic on the modeling of energy dissipation in earthquake solute structural interaction. Today is actually the last part for the theory and formulation, and we are going to talk about the influence of numerical damping or algorithmic damping. So again, we start from the energy balance in a dynamic inelastic system. So as we have seen before, we can derive the global energy balance equation from the global equation of motion here. And then here we have all the physical terms of energy, including the kinetic energy and strain energy and all the energy dissipation mechanisms we have talked before. So here, basically in this black box, like as I noted here, they are all the physical forms of energy. However, when we solve the global equation of motion based on the numerical integration method we use, numerical damping is almost always introduced into the system when we are solving the equation of motion. So here, today we're going to talk about the Newmark family time integration method. So this is a family of time integration methods that are often used in a time domain finite element method. So it is used again to solve the equation of motion incrementally in time. So here is the governing equations for the Newmark time integration method. As we can see, the velocity and displacement at the next time step, which is time step n+1, is calculated from the displacement, velocity, and acceleration at time step at the current time step, which is time step n. And then the equation also involves the time step size, and also the Newmark integration parameters. So using this Newmark. Yeah, sorry. Go ahead.
So the h. So we usually, well, so time step size. So sometimes we call it h, sometimes we call it delta t. Just to
sure.
Somebody's going to ask why h. H is usually used actually for element size, but delta t. This is delta t. Yes, go ahead.
Yeah. You also use as delta t. So by using this Newmark time integration method, it can actually lead to numerical damping or algorithmic damping. Later, we will see that when we go deeper into the equations, but the amount of numerical damping is actually related to the choice of the Newmark integration parameters. One thing when we talk about the energy conservation or energy dissipation for algorithmic damping is the numerical stability, because if you think about it, numerical stability in terms of energy is really the conservation of the total system energy in this case. So traditionally, the algorithm, the Newmark algorithm, was considered to be always energy conserving if the Newmark parameters are chosen to be gamma equals to 0.5 and beta equals to 0.25. Now, however, recently it has been proven that the Newmark algorithm is not always guaranteed to be energy conserving in nonlinear systems, especially when there are high frequency motions and other highly nonlinear, geometric nonlinear or material nonlinearities. So this stability issue has been observed specifically for the case of solute structure interaction. We have, remember we talked about the interface elements. So when a time step size is not small enough, there could be some numerical stability issues. So it is very important to choose a reasonable time step that ensures the numerical stability. Now, however, when we run a really large SSI simulation, we also need the time step to be feasible, because we cannot have like too many time steps, otherwise the simulation will never finish. And also on this note, I should also mention that some energy conserving time integration method was developed intentionally to mitigate this numerical stability issue. However, their use are rather limited, and the traditional Newmark family algorithm is still the most popular one that we have been using for a few decades now, actually.
More than a few decades.
Yeah,
Quite a bit more than a few decades.
Right. So here is just to give you a more clear feel of the numerical stability issue. So here, the model we have is basically two overlapping cantilever beams. One end of them is completely fixed, but the other end of the two beams are connected using an interface element. So then when you lift one of the beam up, and then when you release it, then the beam is going to try to go back to its original location, then try to start a free vibration. But because of the existence of the interface element, it's going to hit the other beam when it goes back to the original location, and then the other one is going to start move. So theoretically, because we are using gamma equals to 0.5 and beta equals to 0.25, and there is no other energy dissipation mechanisms in the system, this vibration should go on forever. So just one beam goes up and then comes back and hit another one, and then just continue this exchange of energy. But the total mechanical energy of the system theoretically should remain constant forever. So when we use a small enough time step, as I'm showing here in this two plot up here, we can see that the motion of those two beams are exactly as we expected. So one beam, after we lift it up, when we release it, it's going to go back to the original location here, and then hit the other beam, and the other beam will move and go back and hit the other one. So this will continue forever. And also when we look at the total mechanical energy for the whole system, we can see that it remains a constant number. It goes through all the whole simulation. So we can achieve energy conservation. That also means that then when we have a much larger time step size, as we can see here, this is...
Han, can you go back a minute? Because I think we lost sound for some reason. Internet wasn't very good. So what you're saying is that in the first case, the time step is small enough, so the energy remains constant, and this is nice. So this is small time step, and then we go to the next time step.
Right. So then we go to the next one, where we have the time step size is 100 times larger than the small one. So now we can, when we see, first we see the motion of the two beams, we can see that at the first cycle it makes sense, but then once they start to interact with each other, which is where the interface elements comes into play, then numerical instability start to kick in, and we can see the motion of them is just start to increase. More clearly, when we see the total energy of the system, we see that this energy is constantly increasing and increasing really fast. So within just a few cycles, it just completely blows up. So in this case, we like observe energy production in the whole system. In other words, it's numerically unstable. So this is just to show you the numerical stability issue that I just mentioned when we deal with interface elements.
Well, I mean, so if I may just add, I mean, it's for interface elements because they're tiny, but it's going to come in for any other element if you use two small time steps. So it's a very good idea to always test this beforehand and make sure that for simple materials, you don't have numerical issues. And then you can maybe start adding tiny bit of numerical damping, but just make sure that you don't eat up energy unphysically.
Yeah, that's right. So we don't usually have like a physical like a solution or like sorry like a theoretical limit on what a time step should be, but usually we should just as Professor Boris mentioned, we should always test that to see okay this is stable, and then we can move on with our simulation.
Yeah.
Okay, so once we confirm that the energy conservation is achieved or the simulation is numerically stable, we can look more into the energy dissipation feature for the Newmark algorithm. So here is a theoretical equation that was derived by Professor Steen Crank. So here is the algorithmic energy dissipation incrementally for a certain time step. We can see that all the physical energy terms are on one side of the equation, and all the so-called algorithmic energy dissipation terms are on the other side. So theoretically, we can use this equation to calculate the amount of numerical energy dissipation for any given time step. So as we can see, using this equation, when gamma equals to 0.5 and beta equals to 0.25, so all the terms on the right-hand side, they will vanish. So there should not be any algorithmic energy dissipation in the system. Now this is consistent with our traditional view for the algorithm. And this is also true when there's no numerical stability issue. But when gamma is larger than 0.5, then algorithm energy dissipation will be observed. So just a couple more points on the numerical damping and the numerical energy dissipation. So we know that numerical damping is very effective in reducing high frequency motions. This is usually actually desirable in a finite element simulation because when we have finite element discretization, we will always introduce a very small amount of high frequency motions into the system, and using numerical damping, that unrealistically high frequency motion can actually be dumped out. But we should also be very careful because if we want the simulation to simulate actually high frequency motions, we shouldn't use too much of numerical damping. So just to make sure that your real response is not being overpowered by numerical damping. So yeah, just continue on that note that unrealistically high numerical damping could reduce the system response to like too much to an unrealistically low level and give overconfidence to your engineering design. So therefore, the Newmark parameters should be chosen reasonably so that the system mechanical energy is not dissipated excessively. And also the physical energy dissipation mechanisms, those two that we talked about earlier, the material plasticity and the viscous damping, they are not overshadowed by numerical damping. Yes, please.
So this is an excellent point. So essentially, it was the numerical damping, algorithmic damping, was introduced to take care of high frequencies because they're introduced artificially in the discretized system by essentially by changing the continuum to discretized points. I mean nodes with masses and stiffnesses, and so but you have to be very careful. So a good engineer, good modeler will essentially do a small sensitivity study just to see what is the influence of numerical damping. And I know this takes this takes more time, but it has to be done because analyst engineer has to understand the effects of numerical damping. And as you're saying here, you do not want to overshadow physical damping by numerical damping. So numerical damping just there to keep it stable and to eat up a tiny bit of those high frequencies, but let the physics, the viscous and material damping take care of the actual proper energy dissipation. Yes, go ahead.
Yeah, right. And just a little bit further on that note, so so now we have talked about basically three types of energy dissipation mechanisms: the plasticity, the viscous damping, and also the numerical damping. And sometimes we have observed in literature that some researchers or engineers try to use one energy dissipation mechanism to kind of mimic or kind of compensate for the other energy dissipation mechanisms. And might so if, for example, if you're looking at the like the peak ground motion or peak displacement, you might actually get something that's okay. You maybe get a false sense that you can use one energy dissipation terms to cover the other. But however, if you look closely, for example, the detailed response of the system, you will see that the different energy dissipation mechanisms actually gives you very different system response. And later we will actually use a rather simple example to show you this point. So the point is that you shouldn't try to use one form of energy dissipation to compensate or to mimic the other ones.
Yes, yes. So this is when we talk about this all the time. So, but I mean, you know, one option is if you do not have capabilities to do nonlinear material modeling, what used to be done and what is still done a little bit, but people are now careful, is to trick the system and put viscous damping to mimic the material damping, the plasticity, which is by far the most prominent source of damping in a civil engineering system, you know, structure, soil, and whatnot. One has to be careful with that, because remember, the viscous part is velocity proportional, and the plasticity part, the material part, is displacement proportional. And so for different velocities, for different displacements, you get totally different. So you're right. So you can maybe curve fit one point, not curve fit, but fit one point, PGA or one of those, but you cannot replicate the actual response of the system. Go ahead, please.
Yes, exactly. And I think another point, maybe just to mention briefly, is that so as we mentioned before, the amount of numerical damping that's in your system is directly determined by the choice of the Newmark parameters. This is an option in our real easy simulator system. However, in many commercial softwares, this is not a choice. So the user does not know like what's the actual amount of numerical damping in the system, or they don't have a choice to change that. So just a note to that as basically a research engineer or a researcher, that you should be aware of this choice, and then you should always run a small sensitivity study to get a better understanding of the influence of that on your simulation.
Yes. Not only as a researcher, but as analyst, as an engineer, you need to know what's going on inside. And sometimes in commercial codes, they'll add a little bit of additional damping just to make results stable. They probably say that somewhere in the manual, but as an engineer, you need to know about that, and you need to do a sensitivity study to make sure that you understand that it's not changing your results in a way you do not want them changed. Good point. Thank you. Yes, go ahead.
Right. Okay. So yeah, so that's it for the numerical damping. And here are the references. If you are interested, please go ahead and read those papers. And I'd like to thank my collaborators and the funding sources. And again, all this energy dissipation calculation are implemented in the real easy simulator. There are examples. So if you are interested, please go to the website and try them out for yourself.
Thank you. So if you will stop maybe sharing, so we just make some concluding remarks. We'll continue with these. We'll have actually a few examples to run and show the influence of material damping, viscous damping, numerical damping, very simple examples. This is coming next, but thank you very much. I think this is going to be very useful. Again, as Hans said, you're more than welcome to actually download real easy and run those examples, and those examples are going to be, they're linked, so the input files are linked, so you can actually use them. Well, thank you very much. Good night, and or have a good lunch. The lunch is coming your way. Yes. So thank you very much. We'll see you next time. Thank you. Bye. Let me stop recording.
Bye.